All right, the next factoring technique that we want to talk about is what happens when we have some cubes. We have some terms that are being raised to the third power, or they're what are called perfect cubes. If that happens, if there's a particular special situation that comes up like that, then there's a formula that allows us to factor this down. To this point, we've only been factoring quadratics, right? Something like x squared plus 2x minus 6 or whatever. I don't even know if that'll factor down, but the point is it's a quadratic. It's a degree 2, right? And then also degree 4s, or just even degrees, right? We've been factoring down. This is a situation where you're going to have an odd degree, and we can still maybe factor it, but it has to be a very special circumstance. Okay? So we're going to talk about factoring the sum and difference of cubes. Okay? The grouping we'll save for the next video. All right? Without a lot of fanfare, and there's not a lot of stuff to go into with this, if you have these particular situations, we factor by a formula. Okay? And what I mean by these special circumstances is this. We have to have two terms, and it doesn't matter if we're subtracting or adding those terms, but it has to be two terms that are what we call perfect cubes. The hard part of this is recognizing perfect cubes. What do I mean by perfect cubes? Well, it's like perfect squares, right? Like 16 is a perfect square, 25 is a perfect square, 36 is a perfect square, because if you square root them, you get whole numbers, right? What else? X squared is a perfect square. X to the 4th is a perfect square. X to the 6th is a perfect square. Because if you square root these guys, you can do it, right? I mean, just divide those exponents by 2. Those are all multiples of 2, so those are all perfect squares. We're talking about cubes. So instead of what number times itself will give you another number, we're talking about what number times itself 3 times will give you a number. So for example, 27 is a perfect cube because if I cube root it, and that looks like this, I get 3. Why? Because 3 times 3 times 3 is 27. So I need a number times itself 3 times that will give me back that original number. 64 is a perfect cube, which is 4. Because 4 times 4 times 4 is 64. Okay? These you're not going to know as well. I mean, memorizing which guys are perfect squares is bad enough. Memorizing which guys are perfect cubes is kind of tough too. Now you'll start to pick up on some of those. But for this, lean on your calculators. Let them help you find how to determine if a number is a perfect cube or not. And if you need help figuring out how to cube root in your calculator, come in and see me and we'll figure it out. Okay? Now, while we're at it, variables. This guy is a perfect cube. This guy is a perfect cube, and this guy is a perfect cube. Those are all multiples of 3. And we can keep going. There's more than just that. But any multiple of 3 is going to be a perfect cube. Because if I cube root it, I'm looking for something times itself 3 times that will give me x to the 3rd. Well, if I go x times x times x, that will give me x to the 3rd. So the cube root here is x. Same thing here. If I cube root x to the 6th, I know that x squared times x squared times x squared will give me x to the 6th. And so the cube root is just x squared. You're starting to see a theme. 3 divided by 3 is 1. 6 divided by 3 is 2. If I cube root x to the 9th, 9 divided by 3 is going to be 3. So we're looking for multiples of 3 to be a perfect cube. And we're just going to divide that exponent by 3 to find that perfect cube. Okay? That's how we're going to recognize it. And that's just going to come from experience. If we find that we have a sum and difference of cubes like this, then what we do is we cube root those two terms and we figure out what those cube roots are. And we can factor these down. And the way we factor it down into a binomial times a trinomial. And the way we create the binomial and the trinomial. The binomial is just whatever we get when we cube root those two terms. Right? And it goes into your parentheses. Here and here. In the trinomial, what we do is we square this first term to make the first term there. Square this second term to make the last term there. And then we multiply these two guys together to get the middle term here. Okay? And this is going to make a little bit more sense when we get to some actual examples. The signs. Okay? The signs. The easiest way to remember the signs is to soap it. Use soap. Always want to use soap. And what that means is S is same, O is opposite, AP always positive. The signs are going to be always, so this is going to be the same. The first one's going to be the same. The second one's going to be opposite. And the last one's always going to be positive. Always, always, always. And so you see it down here. Same, opposite, always positive. Soap it. Okay? All right, let's take a look at some examples and see if we can make it make sense. This guy here, it's two terms, and it's not, and it is a difference. So you might be thinking a difference of two squares like we've been doing before. You can square root 64, but you cannot square root either one of those two. So it's not a difference of two squares. As a matter of fact, it's one of our cube deals. And the way I know that is because the exponent on this guy is a multiple of 3. That plus the fact that we cannot square root it. Okay? So what I got to do is I got to cube root this guy and cube root this guy. And when I do, the cube root of 64 is 4. In your calculator, you can type in the cube root of 125, and you're going to find that it's 5. The cube root of b to the third is b. Now we get into our formula. We need a binomial and a trinomial. Our binomial just comes from these two terms. So we go 5b and 4. Then our trinomial. We square this guy to get 25b squared. And then we square this, square the 4 to get the last guy. And then we multiply those two, 5b times 4, to get the middle guy. And then we soap our signs. This is the same. This one is opposite, right here. So same, opposite, and this guy is always positive. Always positive. So same, opposite, always positive. All right? A little less mess, a little quicker this time. Okay, it's two terms in a sum, so I know it's not going to be the difference of two squares. If I look, I can cube root this guy, and I can cube root this guy. The cube root of m to the third is m. The cube root of 343 is 7. So I'll make a binomial, and then I'll make a trinomial. The binomial comes from just those two terms, m and 7. And then I square the m to get the first term here, square the 7 to get the last term here, and then multiply 7 times n to get the middle term here, 7m. And then we soap the sign. Same as the original problem, opposite as the original problem, and always positive. Okay? Soap. Does that make sense? Finding the cube roots are going to be the toughest part, I think. Okay? Here's one for you to try. See if you can't come up with the cube roots of 8b to the third and 1. And then try to fit them in to that formula. Okay. So cube root this guy, because it's two terms and a minus sign. And I can't square root them. Okay? The cube root of 8 is 2. The cube root of b to the third is b. The cube root of 1 is 1. So, make our parentheses. The first guy is going to be a binomial. We're just going to put those cube roots in, 2b and 1. and then a trinomial. We're going to square the 2b to get 4b squared for this first term, square the 1 for this last term and make it 1, and then we multiply these two guys. 2b times 1 is 2b. Now we soap the signs. Same as the original problem, opposite as the original problem, and then always positive. And then we're done. Now, one thing I haven't mentioned is that normally we'd go back into these parentheses and see if we could factor that, because it's a quadratic. We have a b squared in there, and we would want to try. The nice thing about this formula, it's not that anyone tried to create it this way. The nice thing about what happens with this formula is that trinomial cannot be factored. So we're not going to worry about factoring that trinomial down. We can't do it. Okay? All right. Some more. And now we're going to get away from exponents that are just 3. So more than just cubes. Our process is still the same. Right? 2 terms and a plus sign. But I cannot square root 343. I can square root x to the 6th, but it doesn't matter because this is a plus anyway, right? So it's not going to fit the difference of 2 squares. So we're going to try to cube root both of these. The cube root of x to the 6th is x squared, because 6 divided by 3 is 2. And the cube root of 343 is 7. We've already seen that. So we make a binomial and a trinomial. The binomial is just those 2 terms, x squared and 7. And then we square x squared for this first term here, which is going to be x to the 4th. X squared times x squared is x to the 4th. Square 7 to get 49. And then multiply the 7 and the x squared for the middle and just get 7x squared. And then we soap the signs. Same as the original problem, opposite, always positive. And we're done. We're not going to factor this because we just talked about it. And we can't factor this because it's a sum and not a difference. So we're done. Okay? Another one to check out with you. Because another thing we haven't talked about that we should continue to talk about is that we can always factor out a GCF before we get started, right? So here this guy has a greatest common factor of 2x. And so we get x to the 9th plus 8. 2 terms inside of here, but it's a difference, so it's not a difference of 2 squares. So we're going to try to cube root. The cube root of x to the 9th is x to the 3rd, because 9 divided by 3 is 3. The cube root is 8 of 8 is 2. So I bring back down my GCF, and then I make my binomial and my trinomial. The binomial comes from those cube roots, x to the 3rd and 2. And then I square x to the 3rd to get x to the 6th, square 2 and get 4. Those are my first and last terms of the trinomial. And then I multiply the 2 and the x to the 3rd together and get 2x to the 3rd. Then we soap the signs. Add. So same, opposite, always positive. Okay? And we're done. We're not going to be able to factor this trinomial, and this is a sum of 2 and not a difference. Okay? All right. One more. You give it a shot. Stop the video. You can start it back up and see if this is making any sense. All right. There is a greatest common factor of 4. So factor out of 4 and get x to the 6th minus 27. 2 terms, and it is a difference, but you can't square root 27, so we want to check for cubes. Can you cube root that, and can you cube root that? The cube root of x to the 6th is x squared. The cube root of 27 is 3. So yep, we can factor it into our difference of 2 cube deals. GCF of 4 comes down. Make our binomial and our trinomial. The binomial is going to be our cube roots, x squared and 3. The first term in the trinomial is going to be x squared squared. X squared times x squared is x to the 4th. The last term of our trinomial is going to be 3 squared, which is 9. And then the middle is going to be 3 times x squared, which is 3x squared. Then we soap the signs, same as the original problem, opposite and always positive. Okay?
There you go.
Hopefully that makes some sense. If not, come in and get some help. Your homework's out in Canvas. Have that done by next time.